Okay, guys, we're gonna have one more video. I hope to make it a little bit shorter. So first off, the things I want you to know. I'm hearing a lot from people saying, but what do you really want me to know? Like I'm getting that there's a lot of information. What do you want me to know? Try to make that more clear in this video. So compare measures of center. I want you to be able to look at two data sets and be able to see are they skewed, in which case the mean and the median are not in the same are not the same, or are they fairly symmetrical? And so the blue one is fairly symmetrical. It's not perfect. No data set will ever be perfect, but the mean and the median are both 4. Now let's look at the red one a little bit. It has a mean and a median that are different, and I've used this, I think the same things before, but the more skewed it gets, the more further apart those mean and the median will get. So in this case, the mean is higher than the median because it's skewed to the right. It's skewed to the right, so there's more data on the left. Because it's skewed to the right, there's more data on the left, which means the mean will be eventually, maybe not right away, but the mean will eventually be more than the median, right? So right now the mean is more than the median because it's being pulled by the data. So the mean gets pulled in the direction of the outliers, which is also the direction of the skew. So the mean gets pulled in the direction of the skewness. So that's been a common question. Another common question is about variability. So here I have just a standard deviation showing, which is 2, which is 2, and the variability of the blue, which is 3.09. So the A is the red stuff, right? The variability or the standard deviation is only 2. What will happen, and why is the variability of the blue ones more? Looks to me like you only have 2 choices. Why is the variability more? Variability is more because they're more spread out. So if you think of putting all of your blue dots into a bag, right? So you have, what do we have, 6 blue dots that have the number 1 on them, 6 blue dots that have the number 7 on them, and I put them in a bag, and I take all my red dots and I put them in another bag. So I have 2 red dots that have number 1, 2 red dots that have number 2, 2 red dots that have number 3, 4, 5, and keep going. Then I just randomly pick a number and I say, the number 5. What's the probability that I'm going to get a number 5 from a blue dot? Well, not very likely. It's very high. It's very unlikely that I'm going to do that because there isn't actually one. So my variability will be higher. I'll be less likely to get that. The red dots, I will be more likely to get that if I pick out a number, what did I say, 5, because there's at least 2 of them. So my variability, my chances of getting it are higher. So my variability then is lower. I'm not sure if that helped. Sometimes it helps to think of variability as putting all of your dots put all your dots or all your data points in a bag somewhere, and what is the likelihood that you're going to pick the mean or the median? So the mean in this case, or both of these, the mean in both of these is 4. So what's the likelihood? That would be a better way to say that. What's the likelihood you're going to get the mean? That'll tell you which one's more variable, right? So A is clearly more variable. I said that backwards. The blue ones are clearly more variable than the red ones. In this case, the red or the blue was B. Okay. So as you move things and you make them less variable, now I have a chance of getting the mean. I have a chance of getting the median, the middle number here, when I throw them in. So then my standard deviation got a lot closer to the other standard deviation. Okay. So it's not about your number of choices, right? It's not about your number of choices at a standard deviation. It's about the odds of you getting in the middle. What are the odds of you getting in the middle, right? So again, if I have something that has a very nice, beautiful bell curve, if I have a beautiful looking bell curve, let's make one. What are the odds? Because I have this nice bell curve and it's very symmetric. Where does this one go? Okay, I could make it a little more like that. So it looks like a bell curve, pretty much. My dots are not perfectly lined up. My standard deviation is actually now lower than the standard deviation in blue is lower, so there's less variability now because there's more likely that I'm going to get in the middle. So a bell curve will have less standard deviation than a uniform than a uniform distribution. So bell curves will actually have pretty low standard deviation because you're highly likely to get that middle term. Other things I wanted you to learn yesterday is describe these distributions and find the measure of center. Really easily, think of the measure of center is if you had this on a ruler, like picture this being on a ruler and you had pennies built up on that ruler, right? So you had 1 penny at the number 1, you had 1 penny at the number 11, you had 2 pennies at 3 and 2 pennies at 9. If you can picture that, where would it balance? The balancing point is the mean, right? That's the average, the balancing point. So it would be right there at the 6. That's what I just wanted to mention is think of things as being a balance. And sometimes you'll even see people put a caret where it's going to balance, and that's the mean, okay? So that helps with the mean. The median, you're just going to count in, right? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. You're going to look, and sometimes you can look at the data and just see, oh, well, there's my median. It happens to be the same, but I'm just counting. So 1 is a balance point, 1 is counting. So when I look here, I look for how it's going to balance. 1, 2, 3, 4, 1, 2, 3, 4. So I've got 1 more at the 6, and then I can count over and I can figure out where it's going to balance, right? So the mean and the median, it's going to balance. And you don't have to add up all those numbers. You just have to realize that how far over before this thing balances, right? So got 1, 2, 3, 4, 1, 2, 3, 4, and then there's 1 there. So 1 there. And then I've got 1, 2, 1, 2, and then 1, 2, 3, 1, 2, 3. I think it's going to balance right around here. So if I had a ruler, I would try that and I'd say, yep, I think it's going to balance right there. So that's my mean. I'm also counting in for my median, where I think it will balance. You can do it the way that you know, which is you're adding up four ones plus, what do I have? 5 twos, 5 twos, which is 10, plus 1, 2, 3, 4 threes, which is 12, plus 3 fours, which is 12, plus 2 fives, which is 10, plus 2 sixes, which is 12, plus a 7, plus an 8, plus a 9, and then I would add those all up, right? I'm going to add all those up. That wasn't the best way to show you that, but add all those up and divide by the number of dots, which in this case is 1, 2, 3, 4, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23, I think, if my eyes are right. And I'm doing this fast, but that's how you would find the mean. Why would I, but I probably wouldn't use the mean, right? So in this case, that's how I would find the mean. But what I really wanted you to know was not to find the mean, but which would you use? You would use the median. You'd use the middle number because it's skewed. So what I wanted you to say was I would use the median, and the median is, and I would just count in and find where the median is, and that's how I find that, okay? Look for notes on your What would I find? What would I use, the mean or the median? There's really no outliers here. So I would definitely use the mean and think about where this would balance, right? So where would it balance? So from 1 to 10, that middle number, 1, 2, 3, 4, 1, 2, 3, 4, it's going to balance somewhere right in here. And I have the same number of dots, except for this one dot is at 11. And instead of being at, do I have the same number of dots? I was thinking I had the same number of dots. 1, 2, 3, 1, 2, 3. Nope, there's more on this side. So it's probably more over this way where, but I'm going to count for the mean. I'm going to find my mean. The reason I'm going to find my mean and not my median is because, and where will it balance? So I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So I've got 6 and 6. So somewhere in here, but now if I, let's see, 1, 2, 3, 1, 2, 1. If I move this dot over to here, I'm actually got more leverage, right? It weighs more. It weighs more. The penny weighs more when it's out at the 11 than when it's at the 9. So I'm just kind of saying that even if I moved it, I'm not going to, if I move it here, it's going to weigh less. But if I keep it out here, it's going to weigh more. So 11 weighs more than 8. And in fact, an 11 weighs more than 9. So I'm still thinking about where it's going to balance. And it's going to balance somewhere around the 5. Somewhere around the 5, I believe it's going to balance. You can figure it out exactly, but honestly, at this case, all I really wanted you to know is that that you would use the mean and that my measure of center would be about 5. Okay, let's go on. Describe the measure of, okay, so here it's uniform data. There are no outliers, so I would definitely use the mean. So what I wanted you to write was mean, and I wanted you to come up with where the middle is. So what's the middle between 1 and 11? So where will it balance? And put that number down. So that's all I wanted you to be able to do. Look at those and figure out kind of where they balanced as far as the average goes. Today's work, you're working with this correlation coefficient. I want you to know that when you do your projects, as you move this, right? So the whole idea is that the closer these get, okay, so right now, the way I had them to start, they're just a bunch of random dots, right? There's not much of a correlation there. You can put a line there and that's a line of best fit, but that's not really a very good line. It's not really close to the data, and we know that because the R coefficient, the correlation coefficient, is only 0.3, right? Now, as you get closer and closer, I'm comparing data, and I want to know if they actually have a correlation or relationship as they get closer and closer, as you discovered today, hopefully. If they're really on the line, they get really close to 1 at 0.9, right? Generally speaking, mathematicians, people, I mean, they'll look for a line of best fit, and try to see if they can get one. But if it's a 0.2, it's really not considered very significant because these are just some random points. You would say that's just random. Those are not that's not much of a relationship. But if you can get your data points, if your data points line up and they have 0.8 or greater, it's considered to be a very significant relationship. Okay, so you're looking specifically for 0.8 or above. So if in your project you get a I mean, unless you have an outlier that's very strange, but you get a 0.3 coefficient, your conclusion is probably going to be there is not a relationship between the two things that you're trying to show. Okay, there's not a relationship. Yes, there's a line of best fit, there always is, but it's not necessarily a good relationship. So look for things to be higher than 0.8 to be significant, highly significant. You could go with 0.7. Here's an idea that I had. I did this with fourth period, so they already saw it. So I gathered some data from hockey teams. I went to a website, and I think it was a reputable website, but you'd really want to double check your data against something else. And all I did was compare the points of the Red Wings last year versus the points of the Avs last year. And I took that data and I put it into, I put it into who scored more points, how would I compare it? So one way that I could compare, so if my question is who scored more points, that's maybe part of your stat project. I would look at the mean or the median and tell which one I would decide to use. So here you can see on the side, I looked at the mean of the Red Wings, their W, I mean their R for red, sorry, and I looked at the mean of Avs, which is A for Avs, and I said, well, clearly the mean and the median are not the same. So the data is definitely skewed, right? In fact, it's skewed to the right because the mean is higher than the median. So I know that the data is skewed to the right, right? So, but I would say, so I would use the median, but clearly the median is 13 and 26. So clearly the Avs are scoring more. So I would conclude that the Avs scored more points as a team comparing the median because the data appears to be skewed. So that would be how I would write in my project, how I'm comparing two scores using this measure of center. Okay, so I decided which measure and then I used it. But then my next question might be, who has a deeper bench? And so, and this is the same data. And so I will cut out the starters. So I'm not going to worry about the starters. I'm going to use IQRs, right? And there were 20 data points. So the first 5 people are the starters, right? So they're cut out now, and we're just doing the middle 50%. And I'm going to look at the the IQR of each of them. When I use my Desmos to find the quartile 3 and 1 of each group, I find that the IQR is 20 for the Red Wings and 17 for the Avs. So it's a higher range for the Red Wings than the Avs. So I would conclude that the Avs, but clearly it's also higher scoring, right? Like the medians are still higher. So they are higher scoring than the Avs, but more predictable on the wings. Why did I think that? They're not more predictable on the wings. They're actually less predictable because the range of the IQR, the interquartile range, is higher. So I actually said that backwards. So double check what you're writing, and you guys have partners, so I'm sure you'll catch that mistake. So the Red Wings have less similar people. So because their IQR is higher, it's at 20 and the Avs is at 17. Not only are they lower, but they're also more variable, right? So the Avs have a tighter group, right? All of their players are closer together. They don't have less of those 50% of the people are going to be more reliable. So that would be your conclusion as you wrote your project. What might I wonder next? If I was doing that project on the Red Wings, and I don't expect you guys to do that, but if I was, I might think to myself, what are their ages? Are they the same? Are the Avs younger or older team? And then I could analyze that data. I might ask myself, did the teams play the same teams? And how would that affect their points scored, right? If the Red Wings played harder teams, they might score less, right? The Avs played harder teams and they still scored higher, then maybe that means something. Is this a reliable source? Okay, so check your data. Where'd you get it from? Check some other source and make sure the data is true. This was a COVID year. Did they even play the same number of games? So those are just a couple of questions that I came up with, but you guys come up with questions as a group to question your data and decide whether or not you think it's good data and whether or not you think that your conclusion about it is good. Now, that's how you would compare two sets of data that don't necessarily have a relationship, right? Those don't necessarily have a relationship, but if I want to find a relationship and I want to use that scatter plot and find a correlation coefficient, maybe I would do age versus points scored. Maybe I would do points scored versus salary. That's kind of interesting. There's already a lot of stats out there. For instance, points scored versus ice time. That's already out there, right? You don't have to do that stat. It's already there. So be creative. Find something that maybe isn't a regular stat. Do something fun. Other things to consider, you're looking at the census, compare talking on the phone between 2 years. So if you go on that census website, and I'll give it to you again, you can compare data from Colorado school 20 years ago. Well, I don't know when it started. It might have started in 2010. So 10 years ago, you can compare it to when it to 2 different years. You can compare it to 2 different states. You want to know if the kids in I don't know regions do the kids in California text more than the kids in Colorado? You can look at that. You can look at the difference between grade levels, right? So do 6th graders text more than eighth graders, or whatever you want to do. There's lots of different, there's already lots of data in the census stuff. If you don't want to use the census stuff, there's so many other places to find it, right? Find what interests you. That's what we want you to do. Find what interests you. Okay, I'm going to give you one more ed puzzle, I think, today, depending on how long this turns out, so you can see one more example of how somebody took some data, they put it into Desmos, and they made a conclusion. Since I don't have that example, I think they did a better job than I'll do. So thanks, guys.